So this is example number 1 on boundary layer. So let's go ahead and look at the example. In this particular example, you may want to pause the video and take notes if you need to. What you have in this particular example is you got a steady flow. So let's assume that your flow is going in this direction. It's a steady flow, okay? And it's coming at a velocity u. And we're going to call this, we're going to put some dimensions here. Axis, this is the x-axis, this is the y-axis. And it's separated by a distance h. So this total distance between these two plates is h. And the fact that it's two infinite plates is important because what it's saying is when your fluid first starts, it's starting, but after a while it fully develops and it's completely steady and it's uniform. Okay, so that's the importance of it. What is also given in the problem is that your speed is actually given by u max. This is the relationship, 2y over h squared, where u max is equal to 30.30 meters per second. We know that h, your distance h, is equal to 0.5 millimeters. And we know that everything is, this is water, is acting on 15 degrees Celsius. Okay, and what we want to find in the problem is we want to find the magnitude direction of the shear stress and the set on the set at the center and top of the plate. So if we did this, first of all, if you were plot this flow, it will look something like this. This is what your flow will look like. This is your velocity flow across the two infinite plates, where this is the u max will be this value right here. Right in the middle, this is u max. This would be the value for u max. Okay, so it's asking for, we are asked to find what is the magnitude shear stress. What we learned from the classes that the shear stress equation is equal to du, that's the velocity, over dy. So we just need to find your mu at for water at 15 degrees, and that is equal to water at 15 degrees, mu is 1.3 10 to the minus 3 kilograms meter second. Okay, so this is mu. So we have to just take the derivative of this and find what the tau is in this problem. Okay, so if we do this, so we're going to start with this equation. Tau is equal to mu du dy. And we know from the problem, u is equal to u max 1 minus 2y h squared. Now where the u dy is equal to u max, take the derivative. Okay, so this is the value of dy, du, dy. So that means your shear stress then is equal to minus 8 mu u max times y h squared. Now, note one thing, that when it's asking for, it's asking two things, right? It's asking for the shear flow at the top and the shear flow at the bottom. So if I'm looking at the shear flow at the top, I am looking at the top, y is going to equal to plus h over 2, and that would be 0.25 times 10 to the, you need to convert everything millimeters to meters. In the center, y is equal to 0, okay? So those are the two values that we're looking for. Immediately you can see from the equation that y, that's equal to minus 8 mu u max y h. If I take at the center, y is equal to 0, so tau is going to equal to 0. There's no shear stress in the center streamline. Okay. Now at the top, now for the top segment, we take y is equal to positive h over 2, and that gives you 0.025 times 10 to the minus 3 meters. So then replace all the numbers, you get tau 8, 1.3 times 10 to the minus 3, 0.3 times 0.25 times 10 to the minus 3, divided by, I'm sorry, there's a h square missing there. This will be 0.5 times 10 to the minus 3 squared. And if I solve all this, this is equal to minus 312 newtons meter squared. Note that, so the problem, what we are doing is just remember how we derived this. This equation was derived based on a small fluid element, where this is fluid. This is a fluid. Okay. From this fluid, we said that tau was equal to mu du, dy. So really what's happening is, and it's going in this direction, x and y. So if I was going to draw the wall here, and I just separated, I took the fluid, I took a small chunk of fluid here. What we are really saying is, what's happening, it says negative because that negative value is what's acting on the fluid. Okay, so this is, let's say this is on fluid. .12 pascals. And then I'll change the color. Here at the top, action-reaction goes in the opposite direction. So now tau is equal to 3.12 pascals. Okay, so that's the direction of the shear acting on the wall itself. This is on the wall. Okay. So this is a very simple example on, if you know what the pattern looks like, what the equation looks like, then you can go ahead and just simply calculate this. And this is a very typical problem. We usually know what the flow looks like because of test data. We made the wind tunnel data as well. So in this profile, we got lots of test data, and we can actually model this. Sometimes it's quadratic equation is very popular, and that's what you typically have, where you basically do a curve fit, bunch of data points, and that's how you find the flow. And you can show actually theoretically this is the exact solution for this type of problems as well. So this is just a simple replacement of variables, and where you just have to just plug and chug all the equations and be careful what you're looking for. This concludes this example.